Hello. Um, this is the first lecture on calculus, single variable calculus, and well, yeah. Essentially, calculus is a study of curves and continuity, continuous curves. What is a continuous curve? Trajectory. The trajectory of a particle in space is continuous. Do we know this to be true? True? It is arguable, but to a good approximation, if I throw a ball, the the constituent particles that make up the ball move in a continuous trajectory. So the all of calculus is about uh, parameterizing continuity to parameterize curves, parameterizing and quantifying curves and functions. Function is just a curve, as we will see. And how do you talk about these curves? How do you say what makes one curve unique from another? So, in talking about this, we will find what is called the derivative. The derivative is intuitively the rate of change. So, you may think of a curve that a straight curve, which is just a straight line in space, has a constant slope, the constant rate of change. So, a curve that's accelerating upwards um, has an increasing rate of change, and one which goes the other way around, which flattens out with flattens out, has a decreasing rate of change. Of course, we will quantify all this. We'll move into um, integration, so which is the inverse of what is called the derivative. And so if I know the derivative, how do I compute the function itself? So that's the integral. First, let's talk about functions. A function should be thought of as a machine with a slot. A function f, right, has a slot, and what you put into the slot, you put in real numbers. And so this will give me some output, some value. So for some value for whatever I put inside, it gives me an output value. For each input, there's an output. I can only put real numbers inside, though it's easy to generalize to functions which eat integers and spit out integers. You can even have functions which eat integers and spit out real numbers. Though you can have a function which eats integers and spits out real numbers. So there's often, since there are more real numbers than integers, there are more real numbers than integers because between, for real numbers between 0 and 1, there's an uncountable infinity, right? There's irrational numbers. Between 0 and 1, I think root 2 is between 0 and 1. Root 2 is not between 0 and 1. Between 1 and 2, you have root 2, you have root 3, you have you have a bunch of irrational numbers. So the smallest, you cannot parameterize the step after 1. Right? What comes after 1? It's 0.0000 something. And so the real numbers are uncountably infinite, while the integers are countably infinite. So you cannot, there is no correspondence between each integer and each real number. So we restrict ourselves to maps of real numbers because real numbers are intuitively continuous, right? As I said, what's the next number after 1? You can't really say. But if you had integers, you could easily say that the next number after 1 was 2. And an example of a function is f of whatever's inside here returns the same thing squared. So if I put in 1 here, I would get out 1. 2 would give me 4, 3 would give me 9. If I could also put the square root of pi in here, and it would just give me pi. Um, this is an example of a function. You could also have another function, say, that give me some real number a multiplied by the input. So f of 1 would be just a, f of 2 would be 2a, and so on and so forth. Now, this dot here is a placeholder for whatever I kept in, whatever I put inside the slot of the function. So instead of writing dot, which it's not easy, the dot is not very conducive to being put on a computer. So we use a placeholder variable. Variable called a variable, say x, which is purely for typographical convenience. I could very well have used I use letters inside here, but I could use a dot. Since the function holds for all real numbers, but I do not want to specify. If I specify what the function does for every real number, I have a huge list. I have an uncountable infinite list, and so I would much rather think of a function as a rule. So for whatever you put in here, you get something out, and I represent this by just using x instead of the placeholder dot. It's the exact same. Idea. So now I can graph a function. It's I can, to study the behavior of a function for different values. To study the behavior of the function, I can graph it. It's an easy way to see if the function is increasing for whatever values I put in, the function is decreasing for whatever values I put in, and so on. So before that, note that the sine, the function sine, the sine of an angle is also a function. Because I say if I take sine of some x, where x is the angle of some triangle, of some right angle triangle, we have a sine defined for 30, 60 and 30, 60 and various other angles, right? But does that mean, that does not imply that you cannot have a right angle which looks like, if it is right angle here, I have say 49 and 41 here. This is a perfectly valid right angle triangle, but it is not defined by the standard angles way we have treated a sine so far. Sine is continuously valued because the angle here is also continuously valued. So you can have 49, 49.1, you can have an angle of pi here, and this would be 180 minus pi, so on and so forth. So sine is also a function, and you've no doubt seen the graph of sine, so which we will do right now. So x squared is a function, it's a polynomial. This is sine of x is also a function. Sine is a function also because for each input value of the angle you put in, you want to get some angle out. You don't get an angle, you get a number out. So for each number I put in, I get a number out. That's the definition of a function. Okay. So now I can graph functions in the following way. I have this is my flat Cartesian plane. this is y and this is x, and I have a function f of x. I can graph a function in the following way. For each, so the x here and the x here is same. This is the same x. The horizontal axis is the inputs that I put into the function, and the y-axis is just the values of the function. Okay, so if I have f of x is x squared, so 0, 0, 0. So if f is just x squared, then y and x would be equal at 0, because x squared is just 0 squared is 0. At 1, the function would read 1, so that's the next point. At 2, I would read 4, the y-axis would read 4, and 3 would read 9, and so on. This is not drawn to scale, but you can guess what happens in the middle. It is possible with the if you ask a computer to graph a function like this, what the computer does is it divides a computer cannot handle continuous quantities. It can handle discrete quantities, right? It's a collection of zeros and ones. So it's not continuous. It's broken up into little parts, and so the computer divides the whole plane into a bunch of little parts. So I believe so it becomes like just a list of integers, right? So the computer divides the continuous plane into a bunch of little parts of, say, a bunch of little cells of size A, and if the size of A is less than what I physically see on my screen, that is a pixel, then if the size of A is less than what I see on my screen, what can be rendered on my screen, then the graph I get will look continuous, right? It will look continuous to me. And that's how you can render this on a graph on a computer, and I believe you can. So if you take the inverse of the proton mass, that's about the order that we have right now. So the cell spacing is about it's like 1 over the proton mass squared, or it's just a proton mass squared, something like that. So it's a pretty small number. So even though our mathematical whatever we're doing here is continuous, when you put it into a computer, it's discrete, and when you actually want to graph it, say by hand, you have to do it discretely. But you have to know, but since the real numbers are continuous, the function is also continuous in our intuitive sense. But note that, so to get the other side, okay, y is f. So if I want to get the other side, it's pretty simple. I have to note that f of minus x is also equal to x squared. If I put minus x into here, I get minus x squared, but that's just x squared. So I can just mirror this side onto here, right? So this is minus 1, but the readings here are the same. Minus 2 would read also 4, minus 3 would read 9. So it turns out when you put this into a computer or whatever, you get a curve which looks like this. something like this. Poor rendition, but it's a parabola. I tried my best. But it's zero. Yeah, so that's it. So you can, and as you know, a parabola is a good approximation to projectile motion. If you throw a point particle near the surface of the Earth, it moves in what is approximately a parabola. And so that tells me that I can use this f of x and the properties that the properties that f has to derive properties of actual physical objects. Another example, there's another type of curve, a function that you can graph called a hyperbola. A hyperbola looks just like a parabola, but it's if a parabola is a u, a hyperbola looks like a v. In fact, if you take two poles and you attach a wire between them, and there's gravity acting on the wire, then the wire deforms into a shape of hyperbola. So yeah, you can use functions to model real world objects, geometrical objects, and physical dynamical objects. Dynamical as in, if x you replace here with time, this would be the, well actually, to flip it on its head, but we can do that. You can flip it on its head. Yes. So if you replace x here with time, and f here would stand for the position, this would just become the equation of motion for a particle in a gravitational in a uniform gravitating field, as we will see later. Okay. So now this is the graph for x squared, and I won't construct the graph for sine, but you have to note that sine can take on negative values as well. So sine can take on negative values, and the sine of 0 is 0, and if y was sine of x and the x-axis was just x, then the resulting graph would look something like this, commonly called a sinusoid. Okay. So these are two widely different functions. So as you increase for x squared, as you increase the value of x, either the negative or the positive direction, the value of f increases. Right? It increases pretty fast. It increases very fast. But sine is quite different. Sine is periodic. Right? So if this was the distance between these two, okay, so these two peaks and these two peaks is actually equal, so it's periodic. That's because, well, if you put in the angle, so any angle, if you rotate it by 360 degrees, it's the same. So if you keep on increasing the angle that you put in here, eventually it reaches a tipping point where it's 360 degrees and it becomes equal, right? So it decreases, and then it becomes equal to itself, right? So similarly, the distance between here and here would also be equal. The distance between these two and the distance between these two would be equal, though I haven't drawn it very well. So sine is periodic, but this is definitely not periodic. They're completely different functions. But the problem here, but there is a problem, or an apparent paradox. So the value of you can have, we can call the function f of x sine of x. Okay. But here f is x squared. But and for both the functions, f of 0 is 0. Okay. So now consider the following. I take this function, I take this curve, this entire curve, I take it out of the blackboard, I have it here, I cut it into a bunch of infinitesimal pieces. I cut it so small that I cannot tell the difference between this piece and this piece. Okay, two different pieces, I cannot tell the difference. So I take them and and so if all the pieces are so small that they're indistinguishable, I can take them all and jumble them up and make them look like a sign. Right? So if the only information I knew was f of 0 equals 0, then I can cut up the rest of the function, and I can cut up the rest of the function, the curve, jumble it back up into sine, and I wouldn't be able to know. Isn't that insane? So I could have I could cut I could do the same for sine, and I could make sine into a parabola, the sine curve into a parabola, and I could make a parabola into a sine curve. That seems, is that true? If that was true, then that would mean that x squared would be equal to sine of x. That's definitely not true, right? X squared is sine of x is definitely not x squared. So what gives? And this is, you may have heard of a paradox similar to this called Zeno's paradox. So if you cut the trajectory of an arrow into a million different pieces, each piece is indistinguishable from the other, and so the arrow is not moving at all. So a different rephrasing would be the trajectory of the arrow can be made into whatever you want. And of course, this is not true, and we will. This is where physical intuition fails, and we have to use some mathematics. We have to make some definitions first. We have to know what we're talking about, and we have to make the idea of cutting the function up into a million different pieces mathematically precise. Say I have two values of f that are characterized by giving me two values of x, right? So call them x1 and x2. I have two x1, x1 and x2, and so corresponding to these, there is also f of x1 and f of x2 for the function. Now, if I so what I did was I took my curve, I cut it up into a million pieces, which were all of equal length, and for any two given points, x1 and x2, the length. So if this was, I have some curve that looks like this. So the distance between f of x1 and f of x2 would just be f2 minus f of 1. Okay, this is the distance between 2 points, and of course this is only approximate, but it gets better and better and better as x1 and x2 get closer, which was what I was doing. So I have to take the limit. I have to let x2 go to x1. perform some operation on this that takes x, that makes x2 go to x1, and that is called the limit. The limit for any two variables x2 and x1 takes them really close together. Okay, and so taking them really close together means just making x2 equal x1, or making x2 minus x1 0. So if I take the limit, this really means I am doing one of these operations which are equivalent. So this quantity is quite important. The limit of f2 minus f1 is called a little difference in f. So it's a difference in f, so it's df. Note that d is not a number. Df is a whole variable here, and it's a df is a whole variable. Much like I may write say delta f. Delta is not a symbol. Delta f is the symbol. Df is just the limit as x2 goes to x1, and that corresponds to a really small segment of the curve here. So dx, I can also define a dx, which is the difference between x2 and x1. Okay, but note that here I cannot take the limit as x2 goes to x1, because the limit as x2 goes to x1 of x2 minus x1 would just be 0, because I'm setting x2 and x1 equal to each other. So dx I leave undefined for now, and I take it as the x2 and x1 corresponding to the different values of f of x2 and f of x1. So it's just the values such that they are not equal, right? And in general, d of f is not equal to 0. Okay. In general, it's not equal to 0. We'll see how this is. We'll see what, and that's a fact. If you work with this definition of df, it is in general not equal to 0. So now, the question I'm really asking is, if I take a little df and I take a little dx, is it true that okay, so for my argument to work, for my argument to that a sine can be made into a parabola and a hyperbola can be made into a sine, and so on and so forth, for that to work, df must always be equal to 0. For no matter for what f I use and for what values of x2 and x1 I use. And so df must always be equal to 0. Agree? But so in order to prove or disprove this, I write df in the form df is equal to f prime, some number f prime, or a function f prime multiplied by dx. Note that if prime was 0, since dx is in general, we were taking it to be a small length, which is a non-zero small length. If f prime is 0 for independent of f, then df will always be 0. We will see that f prime is definitely not 0, and actually studying the properties of this f prime of x will give us, so f prime is just df by dx. So let us study so often it is useful to use the notation that dx is equal to some h where h is a really small quantity. So let me just draw other quantities right here. Like this is some two values of f. So this is f of x2, f of x1. The difference would be just this little distance here on the curve. Okay. So this would be x1, this would be x2, and the distance here would be dx. And so if as a function, if all df's were indistinguishable to each other, then that means f prime would have to be 0. And so df would be equivalent to 0. And I also call dx h. It's a common practice to call df yes. So and in order to make so I think yes, I want to rewrite df slightly. So I write it as a limit. We'll leave at the limit. So if x2 and x1 are 2 points and they're separated by distance h, this would just be f of x1 or just x plus h minus f of x times the limit as h goes to 0, and these are completely equivalent. Okay. So if they're separated by a tiny distance h, then this limit is just taking them infinitesimally close together. And now we can write the derivative in all its in this is the derivative. We can write it as, and it is a function because f of x, the df here is not the df there. That's what must happen. Okay. So f prime is the limit as some h goes to 0 of f of x plus h. That's just dh. I'm writing from dh divided by dx is just h. So this is the definition for the derivative. And in general, the derivative is used to differentiate in order to differentiate between any two functions between any two functions. Essentially what it does is that if I know a small part of the curve that the function represents, or the either or vice versa, if I know a small part of a curve, then f prime tells me in which direction I have to rearrange all the little pieces I have in order to build the function back up again. And so instead of having to know the individual points, so instead of instead of having to paint every single piece, instead of having to enumerate every single little piece of the curve, f prime is a rule. It's a rule that tells me in which way they are enumerated. And it makes sense that it's a rule because it's a function. And functions are just rules that tell you how to map some numbers onto other numbers. So now we compute some derivatives and um, we can retrieve some elementary facts about geometry. So for different values of f, for different types of f, different functions, f prime will in general be prime will not be equal. Should that f prime of x, this 2 is a function. Okay, so let's say f prime is a straight, so f is a straight line. Okay, if f is a straight line, it has a form mx plus b for any constants m and b. But this is equivalent to a textbook definition of a it is equivalent to our textbook definition of a linear equation, linear polynomial, linear thing in two variables, linear polynomial in two variables. So if you single out the y onto one, so it looks like a1 ay plus bx plus c equal to 0. So if I take the y there, so you can take the y there. If you single out the y and you write this side just in terms of the x, then it looks like a function is equal to x, where y would then be the function, which is a nice exercise to do. So you can compute the derivative of this. Actually, I think I will leave that as an exercise to you. I'll do x squared. You can do the straight line. It's the same principle, and the result you will get is f prime is equal to m. Yes, f prime is equal to m for f equals mx plus b. So it's quite simple to do, and it's a nice exercise. It's your job to prove this. Anyway, so I will prove the slightly more difficult. F of x is x squared. F of x is x squared. Yeah. So here in the I want to calculate f prime for f is x squared. So I substitute in the I substitute in x squared for in the definition there. Let's see, limit as h goes to 0. Can you see that? Yes. Of f of x plus h would be x plus h whole squared minus just f of x, which is just x squared all over h. Okay, is that visible? I hope it is. So now, note the meaning of this limit just means this is telling me to set h equal to 0 in the end. Right now I cannot set the h equal to 0 because if I set it, then everything blows up in my face. So I can simplify this, and then maybe I can set h equal to 0. So let's do this. X plus h whole squared is just x squared plus h squared plus 2xh. Then I have a minus x squared here. So I'll divide by h. Now these two cancel, and the limit is still there. I just write it as lim. The x squares go away. I'm left with h squared plus 2h over h, the limit is still there. The limit, we cannot forget the limit. It is crucial to our derivation. So here h, this cancels the square, 2xh, 2hx. Is that visible? I hope it is. So 2xh, then I get h, the h here divides this, I get a. That should be visible. So now this is just equal to h divides this, h divides this. So I get h squared just becomes h plus these two cancel and I get 2x. But now remember the limit. The limit, what does the limit tell you to do? It tells you to set h equal to 0. And so I have to take b. I can set h equal to 0 here, there's no problem. So this is just equal to 2x. And so, yeah, it's 2x and it's not 0. Right? F prime is not 0, which is nice. But it also tells me that if I were to stand on the curve and if I wanted to follow my nose all along the curve, then at each point you can say that my step size has to increase by 2 times the point at which I am, right? Or if you were to interpret this as a velocity of a particle, right? So if this is the position, if f is the position and t is the time, f prime would be the velocity of the particle, and so its velocity would be 2 times the time. So if write this in better notation, if r is the position, t is the time, so t squared, this r is t squared, then okay, I'll actually do it. In general, the for a particle that's moving, for a particle in a gravitational field, its position is given by, as a function of time, is given by -1/2 gt squared. So I can compute the derivative of this, right? But there's a minus here, and it doesn't matter. So, what happens is I can just put the whole thing here into the x there, right? The t and multiplied by the constant, I substitute it into the x, and so I get that r prime would equal, so 2/2 into 2 cancel, you get a minus g times t. And it's a familiar, this r prime is just the velocity. The velocity is minus gt. It's quite nice. So the upshot of the whole thing, everything we've done today is that the upshot is that you can have functions. Functions are objects which associate, which take real numbers to real numbers. There are rules for how to associate two different, say, there are rules to associate numbers, But the thing is, you cannot, in general, decompose a function into many different parts, and you cannot construct one function into the other function. And if that's because of this quantity, the f that's because of f prime. And since f prime is in general non-zero, since f prime is non-zero, since f prime is non-zero, every function is unique, right? So the derivative it uniquely gives my function. That is until now. You can have the f prime. You can have functions which have two derivatives. So the derivative is equal, and so that we will study in the coming lectures. And so the f prime essentially tells me how the function changes at each point, and so it's a function which tells me the rate of change at a point. That's the abstract. Thank you.